And today, after the I don't know, whatever you want to call it, day 21 part 2, let's check out day 22. Enough sand has fallen. The sand has been falling as large compacted bricks of sand, piling up to form an impressive stack. The bricks need to be disintegrated. Stack is tall enough that you'll have to be careful about choosing which bricks to disintegrate. Jenga, basically. The elves responsible for water filtering operations took a snapshot of the bricks while they were still falling, which should let you work out which bricks are safe to disintegrate. Each line represents the position of a single brick at the time the snapshot was taken. So this whole thing is a brick. The position is given as two XYZ coordinates, one for each end of the brick, separated by a tilde. Each brick is made up of a single straight line of cubes, and the elves were careful to choose a time for the snapshot that had all of the free-falling bricks at integer positions above the ground, so the whole snapshot is aligned to a three-dimensional cube grid. The cube, three-dimensional cube is a infamous problem from a couple years ago. A line like 222, means that both ends of the brick are the same coordinate. In other words, that the brick is a single cube. Lines like 0010 and 1010 or 0010 and 0110 both represent the bricks that are 2 cubes in volume. 2 cubes in volume? I guess, yeah. Both oriented horizontally. The first brick extends in the X while the second brick extends in the Y. The first brick extends in the X. Oh no, the first brick. Okay, the first example. A line like this represents a 10 cube brick from 1 to 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inclusive. One end of the brick is the cube at 001 and the other end 0010. The ground is at 0 and perfectly flat. The lowest Z value is therefore 1. This will be important. So 551 to 561 is 1 cube, and 021 to 025 are both resting on the ground. Wait, is it? I thought it was XYZ. Okay, 551 is 61 and 021. Ew. So I guess ground is 0 because the snapshot was taken. Ground is 0, but nothing else is. Or ground, yeah, whatever. Anyway, that's awkward. Because the snapshot was taken while the bricks were falling, some bricks will still be in the air. You'll need to start by figuring out where they will end up. Bricks are magically stabilized, so they never rotate. Even in weird situations like where a long horizontal brick is only supported on one end. That's good for us, I think. 2 bricks cannot occupy the same position, so a falling brick will come to rest upon the first. I feel like this is going to be a maze, and then stack a cycle on top of that, and we've got today's problem, probably. Hopefully not. Here's the same example, this time with each brick given a letter so it can be marked in diagrams. I guess we'll give them letters as they come in. At the time of the snapshot, the bricks are arranged like this from the x-axis side. Once all the bricks fall downward as far as they can go, the stack looks like this, where question mark means bricks are hidden behind other bricks at that location. Now that they've all settled, it becomes easier to tell which bricks are supporting which other bricks. So basically, if there's a brick in the spot below the brick that you exist as, then you're dependent on it. Figure out which bricks are safe to disintegrate. A brick can be safely disintegrated if, after removing it, no other bricks will fall further directly downward. Oof. We're going to have to make them fall later, aren't we? Just determine what would happen if, for each brick, only that brick were disintegrated. Bricks can be disintegrated even if they're completely surrounded by other bricks. So all of the bricks that don't have dependencies, basically. All the bricks that don't support another brick. I guess all of the bricks that don't support another brick and also are not supported by other bricks, assuming that gravity exists. I almost feel like I want to write a Bevy app for this. Just parse it all in, throw it into a bunch of cubes, and actually look at it. Figure how the blocks will settle based on the snapshot. Once they've settled, consider disintegrating a single brick. How many bricks could be safely chosen as one to get disintegrated? So there's a bunch of rules here. So how many could be disintegrated individually? So if we only took 1 brick. Okay, well, I think we can do this without visualizing. Do we have to, I forget, do we have to actually make them fall? Okay, we do have to make them fall, it looks like. Yikes. Okay, well, I guess we start by parsing. Part 1, drop this in here. That's not the right place to put that. Big mistake counter goes up to 1. Minutes since last. Silly advent of code mistake. Okay, so we need to parse this into vec3s, I guess. We're going to want glam. I want glam anyway. Choose whether or not you want glam, but I definitely want glam. So I'm going to bring in glam, IVEC3, I guess. And these are all cubes, right? They're not like weirdly shaped. So there can't be one like a J shape reaching under another one, or some weird like T shape sideways or something. reaching into another one. That would be weird. Make this a little bigger. Let underscore bricks equals parse bricks input expect should parse to do debug bricks. Parse bricks is going to take the input as a string slice, return an I result of a string slice, and I guess a vec of ivec3s, right? I don't think these are ordered as they come in necessarily. So we're always going to be able to look at the bottommost blocks and move those down. Something like that anyway. So I don't think we really need to worry that much about this. So it'll be what? I bet we can't do ranges, can we? I think this is multi-Cartesian product for us. So let's start with, we'll get the start and we'll get the end. Separated pair, brick end, what is it? Tilde, complete car, tilde, brick end, input, question mark. And then we'll need the brick end parser, which I'm going to split out because we're using it twice here. And brick end is not going to give us a vec of ivec3s. It's going to give us an ivec3. And that will be, this can be any number of things, I guess. But I kind of want to just do it manually. So to do this, we've got X, Y, and Z, right? Like this. We could just separated list this, but instead I think what I'm going to do is complete I32, and I'm just going to be real silly about this. So we've got X, Y, and Z, as long as we get everything in there. Character complete, I result, separated pair, ivec3 new X, Y, Z, okay with the input. And this is verbose, but very straightforward and easily, deletable or whatever. So there's this, which I guess we'll document actually. We haven't documented anything. Parses an ivec3 from a 1, 2, 3. There we go. So we've got start and end here, which are both ivec3s. We've got the input. I guess we don't need them to be ivec3s at that point, but multi-Cartesian product is what I want. And I think that we get this from just having an iterator of iterators. So what we end up with is start.x end.x. I guess it's dot equals, right? These are all inclusive. This is y, this is z, intuiter dot multi-Cartesian product, collect, and then this will be okay, input blocks, or I guess cubes. What do we call these? What are we calling them in the text? Cubes. I thought collect was going to be able to infer that, but maybe remind me to update later. Let's get this test running for part 1. And the issue is ivec3s cannot be built from a vec of I32s. That's absolutely correct because we should map over this. And I think we're going to get X, Y, Z here, right? We might get an array. I don't remember. Yeah, it's a vec. Can we do an ivec from directly using glam? That would be super useful. ivec3 from, try from all of the other ivecs. Too bad that's not a tuple or an array. I guess multi-Cartesian product really wouldn't know. Fine. It's fine. We can just do R0, 1, 2. I guess these aren't arrays, right? We should just do cube or something. Okay, so then we get everything. We run this. We get 101, 111, 121. That feels like a solo. So this is just one. This is parse brick. I guess we could do struct brick here, right? Cubes is some vec of ivec3s. And this is a brick. Then we grab this, drop it here. Separated list 1, input, well, not input, but separated list 1, line ending, brick, because I'm going to call this brick and not parse brick. Separated list 1 in, line ending in, no debug on brick, which I'm super happy to have. Let's do that. And then we have a problem with results. Oh, this is not brick. This is vec of bricks. Our type signature was wrong. Cool, parse bricks. And then we have a bunch of bricks, 101, 111, 121. I guess these could all be ranges as well. So I'm using individual bricks here. We could also use ranges, but let's make sure that we have the right numbers for our bricks. Do we? Do they expand on this at all? Not really. I guess what is this? 1? Dang, I wish they used the actual input to describe it so that I didn't have to guess. 5s, nope. 3s, nope. That's unfortunate. So what is this? A, B, C, D, E, F, G. How many do we have in the actual input? Is it just going to be like 26? No shot it's 26. So I guess we just won't label them. Over 1,000. Okay. So if we wanted to, we could now visualize this in Bevy, which I feel like I want to. Because if we have the ability to visualize this in Bevy, then we can just kind of visualize it whenever we want. So like maybe visbricks.rs. Of course, this is a little awkward because Z is not up in Bevy. So we got to do some coordinate translation, but that's fine. I'm just going to grab an example. Could do gizmos. Gizmos are fine. Shapes are kind of what I want, though. Not 2D, though. Not 2D. 2D is the wrong. Why am I in 2D? Because I do a bunch of 2D stuff. That's why. So like 3D shapes, but we need, or rather, we don't need, I want the ability to control the material. That's a 2D material. I want this example, I think, to start with. Viz bricks. We don't have Bevy installed, so that'll be pretty easy for us. Bevy is a 0.12.1. I'll just do 0.12. Viz bricks. This adds a custom material, which we don't really need. That we could use a color material, but our cube is going to be 1 cube big, and then we'll have basically a bunch of transforms. So let's grab parse as public, and then brick needs to be public, and we don't really need this material. I just want it. It's fun for me to do shader stuff. So while not a hard requirement, I'm going to bring it in because it'll make it easier for me to have fun later. That's why I'm going to do this. Has absolutely nothing to do with the problem. Assets, shaders, what is it? Custom material, WGSL. And then we just paste this in here for now. Doesn't matter. I guess if you're interested, this is just a color and it samples some texture, but I don't need a texture at the moment. So I'm going to make this none. Canceling due to test failure. That's fine. Inside of setup then, I guess we're going to call this parse, right? Where is our, I guess we could just insert it too as a resource. That would be fine. I want them to be individual bricks though. So we do what? Use day 22, part 1, parse bricks. And then we have to include the string, right? Which is what we're doing here. I think we're doing this in the other bin. It's funny how little I look at the bootstrapping code in here now that I've just written it and it works for every single one. So input as a string slice, and then we use bricks equals parse bricks input, expect should parse. And then let's see, what do we do for this? Bricks.iter, right? So for brick in bricks, we do this cube, and then for cube in brick.cubes, right? Did we make that pub? Let's go find out. I think I did. I'd made it cubes as pub. So if in viz bricks, right? Actually, this is not what we wanted. This is the input, and then here's the bricks. So we parse bricks for cube in brick.cubes, now autocomplete. Thank you. For cube and cubes. Then we spawn a 1 unit big cube, and we have to do this at XYZ. So I think to get this to work out properly, we're going to make Z Y, and then we should be okay. So cube is an IVEC3, right? So cube dot as, can we just do it as a vec3? Yes, we can. Dot XZY. So we're going to swizzle it. And then this is from XYZ. But do we have a from IVEC or from vec? Scale from translation. From translation. Let's do from translation. Brick.cubes.iter and cargo run p day 22 bin viz bricks. And there's one more thing I want to do here, which is randomize the color of each of the bricks. But I'm hoping that this shows us basically a bunch of bricks. Day 22 assets, shaders, custom material import. Is there an import in here? There is an import in here. I don't want the import. We're going to get rid of the import. We don't need this color multiplier as an import. We don't care about imports today. That means that our, shaders, custom material. Shaders, custom material, color texture. Let's get rid of color texture for the moment. Let's get rid of the sampler entirely, because I don't think we're going to need it at all. So this is effectively just a color. And then when we set this up, we can't use it. Storage access doesn't match the shader uniform is weird. Is that supposed to be group 2? That feels really weird. Custom material group 2. Shaders. Where's the custom material import? This one? Yeah. Okay. So that shouldn't have any effect. I am on main. They got moved from 1 to 2 a little while ago. So maybe for us, because we are not, I don't think there's been a release since then. Yeah, there we go. Bunch of cubes. So basically there hasn't been a release since then, and in the next release this group gets bumped to group 2. In this though, I think this is how this works. 0, I think these go to 1.5. I think this is 360, and then I think this is 1. So we basically need to just spread out this count over 360, which we could do with the rand crate. We do need to add rand if we're going to do that. So what is the version it's on right now? 8.5. Chris, why are you spending a bunch of time visualizing this rather than doing the problem? Well, because I find it fun. That's it. That's everything. Let's see. Gen range, I think, is what we want here. Need a semicolon down there. We need the trait in scope to be able to even use rand. We'll call it an I32 there, and then we'll do hue as F32 here. This way we get one of 360 possible colors. Then we actually have to use the color, because if we don't use the color, then it's all gonna be blue. Eiffel 65, anybody? No? All right, so we got a bunch of colors here. Our camera is in a terrible position. I think Griffin has a camera plugin that we can use, Bevy Basic Camera. I think we're gonna be able to just snag this as a Git dependency, bring it in at the top, and then we need to add a couple components to our camera for it to work, as well as the plugin itself. So for our camera, which we're spawning down here, let's paste this, and this is just gonna be the camera controller. I think is the only part we really need to add. I'm gonna leave that as an insert, even though we don't really need it to be. Oop. And then we gotta add the plugin. Hopefully this is updated. Add plugins. Hopefully it's updated. Come on, be updated. All right, it is in fact updated. We do in fact get a ton of bricks. So the other thing that I need to do here is make sure that I thought this let me scroll too, but it wasn't letting me scroll. So let's make sure that we are like X, Y, Z, hella far away. I guess Z isn't, yeah, Z is what I want, I think. I think XZ is really, so this is our actual input as a Lego brick situation. Can we get this in a better view? Like if we do -50, -50, looking at, I don't know, somewhere in the middle of it maybe. So instead of vec3y, I guess instead of 0, let's do bricks.length over 2. I'm just assuming that this is correct. This doesn't need to be exactly correct, so I'm not even trying to make it. So this is vec3 new 0 halfway as f32 0, I think. And now when we run this, it's still massive. Okay, we need to put the camera there too, I think. I should really change this to be the test input and not the actual input. Halfway as f32. So our camera will be there now too. And then this will change depending on what, do we have to turn around here? Well, that was a mess up. Why was that a mess up? Right, because if it's X and Z, then Y should be vertical. That is pretty good though. I always forget if we need the hash for hex or not in Bevy. So this is what we spent our time on. Congratulations, everyone. Oh, that's funny though. Okay, maybe we do the test input and just see what it looks like so that I have a reason to have done that. So we'll put the test input here, string slice equals this constant, and let's make this test input. And let's make it a little bit closer since it's gonna be smaller. Wait, 1, 2, 3, 4, 5, 6, 7. We don't just have 7 of them, do we? Because 1, 2, 3, 4, 5, 6, 7. I guess we do just have 7. Why am I so low to the ground on this? Oh, because I have to do it the other way, don't I? That doesn't seem right. Why did I make this count? Oh well. Bricks.iter. I guess that's technically not halfway, but whatever. I guess technically this would be what? Bricks.iter, flat map, cubes, and just cubes.iter, or just cubes, I guess. And then what? Max by? Is that even a thing we can do here? Why is flat map complaining? Cubes is because brick.cubes. And I think max by comes from iter tools, right? Cubes has a vec of ivec3, which does not implement copy. That's fine. We don't want to copy it anyway. I want to iter. And then this is max y. This is so much effort. This is going in the thumbnail though. This is 100% creating the thumbnail for this video later. Option? No, let's unwrap this. There has to be one. Oh, also we need .z, right? Technically, because it's z up in our example. Again, the wrong direction. Because I made this negative. Why did I make this negative? Okay, so now we have a visualization. I'm not sure I'm happy with the camera. I don't know what I'm doing wrong. I guess looking at is Y up, right? Transform looking at returns a new rotation so that transform forward points the target position and transform up points up. So up is a vec3, which means that Y is up, which is what we want. I guess technically we could just make this X up. There's an idea. So the other thing here is there's a standard material, yada, 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 standard material. Let's call this STD, or I guess materials STD. And then instead of this, we would do something very similar. It's gonna be a standard material, and this is gonna be materials STD, and then this is gonna be default. And I think color should be on standard material. I don't actually remember. It's gonna tell me in a second. I think this is, what is this called? I guess it's base color now. So if we run it like that, then we do get a little bit more. We unfortunately don't have a light in our scene. So it's going to be very dark, but you can see where like the light is kind of shining off the bottom here. Let's get at least one light in our scene, I guess. In 3D somewhere, there will be any of these really will be, go with lighting, pick a random light example out of here. I guess that could be PBR bundle too. Let's also get this plane in here. That's actually something I was gonna do and then didn't do. So we have a plane, and that should be the base, or I guess it won't be the base because I did it wrong. Plane from size, white, perceptual. Might be in the plane, actually, now that I think about it. We do, however, need a light. Ambient light. We could do ambient light. Spotlight. Point light. I think I want a point light. Let's do some ambient light, though. I don't really want... I guess orange red is fine. I don't really want orange red. Directional light. That's what I want. Oh, I guess we do need to bring in some of these constants. Pi, F32 const pi, shadow builder, just because it happens to be here. We could use the defaults, it doesn't matter. See, so now we're getting a very harsh light onto these, but we do get to see the, like, one side and the other side. I don't know where our plane went. I think looking at 0, oh, right, because I put the thing on the ground. I think we want that. And then if I get the types correct, then we get this, which gives us a ground and our stuff. So that's kind of cool. Make the plane a bit bigger. Do we want it to be white? Make it a little bit darker. So if I remember correctly, the camera plugin we used, it does allow us to move around a little bit. So we can do this. It's a little awkward, right? To like go up and down like this, but we get to see a little bit more of our like stuff going on here. There are actually shadows that we can see, which is kind of cool. I think I like it without the standard material, but okay. So now that we've done all of that, we are going to have to move what? Like those two bricks aren't connected. Looks like most of these aren't connected, but there will be one just on top. As long as we got the orientation right here, which I didn't even check because I was too busy. I think that even though there is some space below this one, that counts as ground. So we're going to end up with, yeah, I guess all of these moving down. Is that correct? So 101, 121. So remember, this is Z up. So these are on the ground. So that looks correct to me. Bring the visualization back because I can't look at this and do the thing at the same time. So this one down here is our ground. And then we go up one, up one, up one, up one, up one, gap 2. So I think we're good here. We got it correct. Okay, we've done nothing but visualize it. So I guess, all right, so we got a fun little visualization of our stuff over here while we're doing this. Ridiculous. Okay, so now we have to actually make sure that these all go downward, right? I think that's the part of the problem we're on. Let me get rid of the Bevy stuff. See, actually, do we actually have the side? So GG across, I guess that would be like this side, right? So GG across, hit, half, GG across, hit, half. This is from the other side, effectively. This is actually from the lit side. This camera is slow. I could have fixed that, but I didn't. So we are looking at it from this side. We've got down, across, 2 like that, down. And we've got down, across, 2 like that, 2 across, and then A, and then the bottom. So this is our grid. It is correct as far as I can tell. So let's get into actually doing something with this. How do we determine if a brick can fall? I guess for the entire area, we try to move it down, try to move it down, try to move it down. And we do that from the lowest to the highest. And we do that from the lowest Y position. So maybe we sort these before we do this. So like itertools has sorted, but I guess we do kind of want this. Sort all the iterator elements. Yeah. I mean, I guess creating a new one is fine, right? Sorted by v.z, right? Start running our tests. We have to build so many more dependencies now that we have just like a full fat, everything enabled Bevy app. That's too funny. That's why I have everything in separate days, because the dependencies don't need to match or crossover. But in this case, they kind of do because we have binaries here. Closure is expected to take 2 arguments, but takes 1 argument. So what is this? A and B. It's like this. Sorted bricks equals that. Debug sorted bricks. I guess it's a.cubes.iter.min, right? Where we map cube to cube.z. Then we compare that to the same thing for the other one. Comp. Get my braces correct. Okay, iter map cube.min, right? So we want the 2 minimum most values. And this needs to be b.iter. And then both of these need unwrap on them, right? Because they both need to have a minimum. And the comp needs to be a reference. And then we get what? 1, 2, 3, 4, 5, 6, gap, 8, 9. Okay, I think that's good. Sorted bricks dot iter. And then what are we actually doing? Sorted bricks is kind of our state too, right? I guess we put these all in. I guess we do them one by one. We put them all in one by one. So let's do fold where a vec, I guess it's a vec. It doesn't have to be a vec, does it? I think I'm just going to make it a vec. We could do this with ranges. It would probably be easier. I just want the cubes for visualization purposes, right? So we've got a brick. We didn't collect this, did we? I guess it doesn't really matter. Into iter, fold. Then we have vec and brick, and we don't know what vec is yet. I guess we don't reduce, right? Can we rely on the fact that the first brick that we're going to have is at ground level? I don't think so. I think they're all going to be in the air. We cannot rely on the fact that we have a ground level brick, right? Because that would be 1 tilde with a comma before it if it existed. So we do have a brick on ground level. Looks like we have multiple bricks on ground level. So given a brick, right, we have a bunch of cubes. And those cubes each have XY positions. We only need the bottommost layer of cubes, and we need to find the topmost brick that exists in our cube vec for those XY positions, or XY positions. Converting between Z up and Y up is going to be confusing in my head. So I think we take our brick, we look at the cubes, and we go for the min, right, .iter, .map. We can't min all somehow, right? Min set, return all minimum elements of an iterator. Min set by key, min set by key. So min set by key, and then the key is what? A function where we access it. So it's cube.z, right? So that's min cubes, which gives us a vec. We do need to return everything here. ivec3, min cubes. So we have our min cubes and we have the xy's for the min cubes. I think the min cubes is always going to be a very small number. So if we min cubes.iter.map cube.xy, right? Swizzle it, collect. Then we have the xy positions of all the cubes. And this is going to be an ivec2, I think, when it comes out. And I think that has to be owned. Yeah. And then we do accumulator, iter, max. I guess is it max by key? But it's max by key only if it's in this set. And we're no longer guaranteed to be sorted. I guess we only need to find the highest cube. So act.iter, flat map, brick.cubes. And then we find the max z. But we filter here for a cube where the min cubes xy contains cube.xy. And I guess technically if we find them all, we don't have to recurse down, but I don't know that it matters for us right now. We do max by key cube.z. Oh, this isn't the function. brick.cubes.iter, I guess. Wait, why is brick in ivec3? This needs to be a vec of brick. So that all, and then, so given this could return us multiple maxes, but I don't think we care. And further, I think we only actually care about the z's. So we can just run max here, because if we filter map here, then if it contains xy, then we can give z back. And that gives us the max z underneath, which means the z we have to target is z plus 1. Assuming we did find a max. I'm going to assume we did for now. Expect a max to exist. So then brick.cubes into iter.map cube, mute cube, cube.z equals cube.z minus, we need to do this once for one of the cubes that we have first, right? We have the lower bound of cubes already, but we don't have the z's. So let brick z equals min cubes dot next dot unwrap dot z, iter next unwrap z. We get 932 there, and it's cube z, diff equals brick z minus landing z. So landing z then, if we are, say, if we have a brick under us that is at 1 and we are at 3, then we want to find the 1 and we want to know we're at 3, and 3 minus 1 is 2. And if we have one above us, then it's 4 minus 1 is 3. So is it just brick z minus landing z? No. Let's see, if we're at 6, right? Because this upper one is at 6, and we have 8 and 9, right? 8 minus 6, which isn't what we have. It's 8 minus 7 is 1, and that's our diff. So 8 moves down 1, 9 moves down 1. I think that's right. Landing z is already plus 1. Cube z minus diff, cube. I guess we could do iter mute here for each, and then we don't need to return that. We can just do that. And then can't be borrowed as mutable because we didn't borrow it as mutable. We owned it here, so we have it and we can do whatever we want with it. Brick is a shared reference. I guess it is. I guess we're going to be cloning this. Or I guess not cloning this. We could clone this though. If we iter, we create a bunch of cubes, let new cubes equals this. This is not for each anymore because we're not going to mutate that. We're going to collect that. We're going to accumulator.push brick cubes, new cubes. The accumulator is not mutable. Mute. And then fallen bricks. The fact that there is no max is interesting. Is that the first number, the very first? Flat map, filter map, inspect. I guess there is no value coming out of this. I thought the iter just wouldn't run if it was empty, but I guess it still hits max at the end. Interesting. So I guess we do assume that we have something here. Do we default it to the ground? I think we do. Let's leave this dot max unwrap, or what was this supposed to be? 0. So unwrap or the floor, at which point we get a bunch of stuff. So fallen bricks, 1s, so 3 1s, and then we have 6 2s, right? So 2 2 2 2 2 2. That's correct. And then we have 2 3s, so 6 3s. 1 2 3 4 5 6. That's accurate. And then we've got the 4s, and then we got a 5 6. That is correct to me. So what were we actually supposed to do? I'm having so much fun just writing brick code. How many can be safely disintegrated? Oh, wait. Yeah, we had to settle them first. Okay, that was, I was going to be like, oh, we didn't have to settle them. Dang. So now we have to figure out which ones are supporting other ones. So basically which ones have an XY that is directly below another brick. And I think these are, I don't know if these are naturally in order. I don't know if it matters either. So fallen bricks.iter. I feel like it would be nice to pre-scope this. Like if this wasn't a vec, if this was a hash map, then we could definitely, we could build a hash map here of cube to brick. If we give each brick a number, numbers are arbitrary, just like the points on whose line is it anyway. So if we do an enumerate here, maybe we fold this into a vec, and then we do fallen bricks.iter enumerate. This will give us an ID for each of the bricks. The ID is not like stable, so we can't really use it to refer to them. We could have done that earlier, but we didn't. Maybe that would be a better way to do this, but right in our parser, if we had brick and brick had an ID and we just incremented some ID over and over, I guess it's the same thing we're doing here really. If we ever want that ID, we could always just move it back up. So enumerate map ID brick, right? And then for every key that is the XYZ position, I guess, because it all matters. So maybe this is flat map, and maybe this is brick.cubes.iter.map cube.xyz, which is a function, which is our swizzling, and then the ID. And we collect this into a hash map because we don't care about the order. And actually, we can't actually keep IVEC3s as the keys in a B-tree map, which is the most of the reason that I've been using a hash map anyway. And this is going to be usize, I guess, because the IDs are that. We need to bring in hash map. Oh, that's a Bevy utils hash map. That's not what I wanted. I wanted standard collections. That's a shared reference. So let's swizzle it up. Is there a reason we have a problem with that shared reference? May outlive ID. We aren't using this. Oh, I should talk about what I just did. I had an issue here. Closure may outlive the current function, but it borrows ID, which is owned by the current function, which is fine because we're running enumerate here, which means we're generating an ID that then is owned by this closure. We have a closure inside of it. Our inside closure needs access to ID, which is currently owned by the outside, but we can just make it move in and be fine. So this is going to be what? Let brick map is going to be IVEC3s and usize. So this is going to give us the cube position for every IVEC3 and actually the brick that it's associated with, in which case we can take fallen bricks, iter, filter, brick, and this is just going to be .count at the end. Let dissolvable equals this, get that nice formatting to happen. We need the top level bricks this time, which we just kind of did. It's going to be max cubes XY, right? So instead of min, we want max, and we need, I guess, the other one too, this one. A lot of collects happening here. Not too worried about it right now. To do this, this needs to be max cubes and max set by key. And I think that's all good. And then for each of these max cubes, right? So we don't need to collect here. For each of these max cubes, we need to construct the set that is above it. So we need the IVEC3 that is cube.x, cube.y, max z plus 1. And then this is going to be brick map.get is sum, because we don't need the count of the above. We just need to know if there is one. ivec3, max z doesn't exist. Max z equals max cubes 0.z. That'll just exist, because if we're dealing with a cube, then we have to have a cube there. Or if we're dealing with a brick, then one cube has to be the top cube, at least. So we do the get here. I think the get has to be a reference. That's why we're running into an issue here. And then is sum, and that gets filtered back, right? No, this gets mapped. So are we looking for any here? We're looking for not any, I think. So if not any cube in the top layer of cubes for a brick exists, wait, if I didn't say that right. If any cube in the top layer of a brick has a brick above it, then somebody is depending on it. But we want to filter for the ones that aren't dependent on, and then we want to count them. So dissolvable count should be that. Why did I put input there? Because my brain is frying. That's why. I don't know why I put that there. Unreachable, that's part 2, I think. I misspelt my own variable. Okay, so that claims that there's only one, but we know that's not right? Because 5 can be. I guess the other thing is if there is a brick on the same layer that holds up the brick that we are concerned about, then also, and that is the case for 1, 2, 3, 4 of them. So that'll add 4 for us. So I guess this isn't any to start out with, right? Do we have the IDs here? I guess we do, right? Cubes we support equals this, and let's not is sum, right? To do here. Cubes we support is this. This is an input iterator of the usize, so the usize is the IDs. If cubes we support is empty, what, return false? True. If we don't support cubes, that's still input iterator. Let's call this unique collect, and we'll call this a vec of usize because they're IDs. And we have an issue because we have option usize. I guess we flat map this. We don't need the response. We need the sum to be gone. So flat map cube, I guess filter map, right? Then we have a vec of usize, change to reference. We'll just clone that to get that off because it's cheap to clone. And we are at to do, which is great. We now need to check to see if there are any cubes on the layer above us that have a brick below them that are not us. So we need to do a reverse lookup, right? So not only do we need brick map, this is brick to ID, we also need ID to cube. So we want brick to ID map, right? We want to iterate over that. We don't want to enumerate because we already have it. We have the ivec3 and the usize. And I guess we want to fold this. And this will be a hash map. And in here, we don't need this stuff. We need map is going to have to be mutable. Map.entry, and the thing is going to be id.end modify r.push brick. This isn't brick, right? This is cube. So let's start off by doing that. And this is cube id. This is push cube. So or insert vec cube, right? Mutable reference to a vec. What is the problem here? Do I just not mention it as mute? Type must be known at this point. Yeah, okay, fine. This is a hash map of usize to reference to ivec3. And we need to use turbofish syntax here. And this probably needs to be dereferenced. Push needs to be, this is not right because this is going to be a vec. And we don't collect this into that hash map because this is already done. We have our ID to cube map, which should be a vec of all the cubes for each ID, which we already technically have, but we had to really redo this because I chose to enumerate here instead. I'm trying to modify code as we move forward rather than going back and refactoring. So fallen bricks, iter, cubes we support. If we have cubes we support, okay, so if we support cubes, right? If the vec of usizes is a thing, then we need to check those cubes and see if they're supported by anything else. If they are, then we're good. If they aren't, then we are not good. So our ID then is really easy to get right here. If we do max cubes 0, and this is, what did we call that? Lookup ID to cube map. I guess we can just index in here because we're not really worried about it. Shared reference. Oh, not a shared reference. What is the issue there? Dereference maybe? Expected use size found ivec3. True. This isn't what we want. We want the other one. And this is not brick to ID map. This is cube to ID map. So our ID is cube to ID map with this cube that we just grabbed. So there are some cubes we support. We iterate over those. We're probably filter mapping here. We're filter mapping for the cubes that support them. specifically the IDs, right? So we've got cube to ID map. We can pass in cube and get an ID. That is not necessarily what we want to do right here because we need the supporting cube. And that is cube.x, cube.y, cube.z minus 1, right? Cube to ID map dot get on this because we don't know if it exists actually. So it's an option usize. Actually, that might just be enough because if we do a cube that we are supporting and we look below that cube and we get the ID of whatever cube is below it, the ID of the brick of the cube below it, then if we don't find one, we don't have one. And if we do find one, then there is one. Why are all of these red? No field Z on usize. Cubes we support. Oh, we need to get the cubes that we support actual. I guess we already did that work up here. So we're kind of just duplicating it. Not there. Where did we do it? Oh, well. Yeah, cubes we support, filter map, cube to ID map. This is bricks we support, and that's brick ID. And then this is going to be ID to cube map, brick ID, which has to exist because otherwise we wouldn't be using it. This is .get, but because it has to exist, we can just index and we're fine. So then we get a hash map. Wait, we get a hash map? Did we build this up wrong? Fold into a hash map. That is a hash map. We should get the vec if we do ID to cube map. Oh, it's as index output. Okay, that's fine. So we do get our vec. Then we need a cubes.iter.map cube, right? Like this. And then this needs to go in. And if we're getting here, this is a filter map. I don't think this is. Then we should do this. And then there's a problem with our indexing. Move occurs. Cannot move out of hash map. That's fine. I don't really need to move here. So we do .get. We get the option vec, whatever, but this has to exist, so we have to unwrap. And we get the shared reference to the vec. Cubes iter filter map. This is going to be .uniqued, right? And that should give us all of the IDs. Okay, so we take the brick IDs we support. We grab the brick ID from the cube map, which gives us the cubes for that brick. The cubes for that brick we iter over, and we filter out any of them that don't have a block below them. But if they have a block below them, we get the ID of the brick that is part of that. So for each brick, I guess we do this, which gives us the IDs. I think we want the unique here, right? For this brick of cubes, we want the unique IDs of the supporting cubes. And we want the count of that to be greater than 1, right? And this isn't map, this is filter, and this is bricks we support iter.count. And this is the count of bricks that we support. No, it's the count of bricks we support, but for each individual brick, we need to know if that is a brick that is supported by somebody else. If the cubes in that brick are supported by more than one, then this is one we count as a brick that can be, as a brick we don't need to care about. So maybe we don't count that, in which case it would just be 1. We would filter this out, which means that the bricks that we are critically supporting needs to be 0 for this brick. Yeah, for this brick to be. So if this brick is not supported by any other bricks, I feel like this should be any, not filter. If the brick we support, right, has cubes that are supported by multiple bricks, then it can get filtered out. We're left with the bricks that we support that are not supported by anybody else. If there are any, then we cannot dissolve. My logic is clearly wrong on this. Bricks we support, right? So for all the bricks that we have in the pile, we filter on brick. For that brick, we get the IDs of the bricks that that brick supports. If those bricks are supported by more than one, then they don't count. So if we filter here and we inspect the brick, there should be a list of independent bricks, right? So we should get both bricks on the second layer. That's one brick on the second. That's one brick on the second. We should get both bricks on the next layer. That's 4. We cannot get 1, 2, 3. We cannot get this 4th brick, but the 5th brick is definitely. So the 4th brick is our issue. Why are we getting the 4th brick is the big question. Because Chris is confused at the logic after having done 22 days of Advent of Code. That's why. Okay, let's inspect what's happening here. These are the brick IDs. So when we inspect, we're going to unfortunately ID to cube map it. Okay, so we end up with 1, 2, and both of those are in the second. That's it? I was expecting more output than that. So bricks we support then is potentially getting the wrong list. So bricks we support 1, 2. I'm assuming this is 1 and 2. Just total guess here because they were sorted at one point. So we ID to cube map get this inspect, and the count here we want to be 0, but it is 2. Okay, so bricks we support 3, 4, 3, 4. That is wild. 1, 2. And then this is the final. So these two support 3 and 4. So that makes sense. And then those get filtered out, right? So for the brick ID, the cubes, we get the ID of the supporting cubes, which we have to unique. Maybe we inspect supporting cube. So bricks we support 1, 2, supporting cube 0. So 1 and 2 are supported by 0. That is true. Supporting cube 0. Bricks we support 3 and 4. 3 and 4 are both supported by 2 and 1. 5 is supported by 3 and 4. 0, 1, 2, 3, 4. 5 is supported by 3 and 4. 0, 1, 2, 3, 4, 5, 6. 6 is supported by... Why does it think it's supported by 5 and 6? Oh, because we don't get the minimum. That's why. Interesting. So where's our min? So when we do this, we need to get the min cubes, I guess, for our brick. We can't just do it on all because we're looking directly below. So this is a lot of logic. Probably should have been easier than this, but I spent a bunch of time visualizing. So supporting cube 5 and 6 should not be true for 6. So when we do the cube to ID map, that's fine, right? But this supporting cube, these cubes need to be these mins. So I think we can just do min cubes here, right? We just do cubes.iter, right? And then min cubes, and min cubes is this, and that should pass us. That passes. Great. Wonderful. Let's run this. Actually, let's get rid of our inspects. So now we're going to run part 1, claims to be 430. That can be disintegrated. And that is a gold star. We got it. It was just a bunch of work to figure out. I probably should have done that visualization afterwards or something. Okay. Okay, disintegrating one at a time isn't going to be fast enough. While it might sound dangerous, what you really need is a chain reaction. You'll need to figure out the best brick to disintegrate. For each brick, determine how many other would fall if that brick were disintegrated. Disintegrating A would cause all 6 other bricks to fall. F would cause only 1 other brick, G to fall. So what, we basically want the lowest brick, the sum of the number of other bricks that would fall. So we want to find the lowest brick that can disintegrate, or that can't disintegrate, actually. Wait a second. Wait a second. Let's visualize this back in our... So we're going to look at this, but we're going to do it on the production information. So let's input, visualize the bricks. Look at how many bricks we have. And then we go down the bricks, 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 down the bricks. It's a lot of bricks. I should have made this camera move faster, but that is my fault, not your fault. So, still going. I'll see you at the bottom. Okay, so we're at the bottom. This is a non-trivial like situation here. I don't see any brick here that would be obvious to drop out. And I don't see any brick that is like, actually these aren't collapsed anyway. So there's that. Maybe we should be able to visualize the collapse, but so let's grab our part 1, stick it in part 2. And I guess we could go down from the top, tracking the graph of dependencies. If we go for every brick and we check to see what it depends on. So we go top down. I guess we could go bottom up too. It doesn't really matter. Then what? We want a max spanning tree of that graph. Pathfinding had something. Look at undirected. We basically need the node in the graph for which there are the most dependencies that also is the only one that those nodes depend on. So we can build the graph in 2 different ways, right? We can start at the bottom, which is kind of like the leaves. So I guess we start at the top and then we check to see which blocks the top depends on. And we end up with this expanding tree. And then we keep the counts for every block. How many blocks are there? How many bricks are there, actually, is a question I have. Looking at our input, there are 1,232, which are all look like they are pretty reasonably sized. So if we get the bottom of any block, right, and we figure out what it depends on, then a valid block to remove is a block that only has 1 block above it, or is the only dependent for the blocks above it. Oh, we don't even need that. We need the sum of all of the bricks that can fall. Eek. So we actually need to calculate this for every single one. So I guess we work our way down. First of all, we need to build up this graph. So maybe we use pet graph. I don't know that there's anything really worth using. I think if we build this graph, we can at least dot it out, look at it, and then I think we just iterate over everything, right? I guess technically all the points we can condense that would be, that's not true. Return the number of connected components of this graph. So we have two graphs here. Connected components graph 2, add edge BE, connected components 1. This is for cycles and stuff. Return a vector where each element is a strongly connected component. For an undirected graph, the SCCs are simply the connected components. Strongly connected components are marked. Every vertex is reachable from every other vertex. That is not what we're looking for. I think depth first? In a directed graph with root node R, a node A is said to dominate a node B if and only if every path from R to B contains A. I think that's actually what we want. This is for the nodes that are dominated by a given node. This is the dominance relation for some graph in root. I think this is it. So I don't think I'm going to use anything else, because taking a second to think about this, right? We've already got the code that moves bricks, right? Fallen bricks is this, and that's not too bad. So we could run this 1,200 times. I am pretty sure that our part 1 doesn't take that long to run. So the benchmark for part 1 runs in about 8 milliseconds. If we have to run this 1,200 times, that's about 10 seconds. So I think I'm okay with that trade-off. It will at least work. So for part 2, I guess we want to move this out into its own function. And then the rest of this doesn't actually matter, because we don't actually need to care. We only need this. So let's make a fall function, leave this here. And we need sorted bricks, which is what, a vec of ivec3s, if I remember correctly. I don't know that that's true. No, it's a vec of brick. And then this needs to count how many fall. That is bricks, not cubes. Which if we store the bricks in hash sets, the cubes in hash sets instead of vecs, that comparison is really easy. And then for sorted bricks, right, it's just for brick and sorted bricks.clone. So this is new bricks, right? And new bricks, I guess dot position. So this is iter b equals brick. We don't have that implemented currently, but we will. This will give us the index. Then we remove the index, right? This will be into iter. Is it into iter? I guess we just filter if it's into iter, right? For b not equal brick, that's not index. That's letting, this whole thing is new bricks. Dot clone, dot into iter, dot filter, collect, and then it's fall new bricks, and that's fall count. I'll leave a debug here, and then we need to do brick as hash sets. So I think I'm going to cheap out on this, and for bricks, I'm going to let bricks equals bricks.map or dot iter into iter dot map brick. Well, actually, we don't need to cheap out on this, because where's brick? Brick is here. Probably hash set would have been better for this anyway, starting off. Standard collections hash set. Then all this just keeps working, right? And this gets eq and partial eq. And this is double reference to single reference. Then we collect into a vec of bricks, right? We fall. Not bench, test. Where's test? Part 2. New bricks. Where are we? Sorted bricks. I don't really want this to need to be a vec. Iterator item is a reference to a brick here. I guess we can just keep this in there forever, right? We don't actually need brand new bricks here. Dissolvable, let's just do 0. And then sorted bricks, value borrowed here after move, yes. So we'll clone on the loop, and then we'll clone inside of the loop, and it doesn't really matter to us. We don't really care. Fall count here is always unit, because we aren't doing the counting yet. So here we're folding. We could do vec count. I just realized these bricks need to fall first. Dang. We sorted them, we parsed them, but we need to actually make them fall once beforehand. Fallen bricks, of course, doesn't return anything currently, but it needs to. So we'll return this tuple of fallen bricks and num falling bricks. I don't know why I did that. Tuple, a vec of bricks, which is the same life as the other bricks, right? I guess not, actually. The fallen bricks are new, so maybe these should be owned anyway, no matter what. So at the very least, this needs to be owned. What is this now? This is different. So vec like this, and then fall count, type the tuple, and that returns those two things. And then when we mute fall count, we aren't counting yet, so we don't necessarily want this to be a reference, right? turn this into our full first set. I wanted to do these like that. I think we still can. Okay, so fallen bricks can now be here. We don't care about the number that fall when we're doing it. This is going to be fallen bricks. We can't clone bricks because we didn't implement it. We can, but do we have to? Fall gives us back those brand new bricks, which we don't really need to keep around. Looking at all the types as I do this, need 2 ampersands here now. Fallen bricks is an issue for the same reason it was before. This gets a free ampersand on it. Fall count is still not being used. And then we have a debug out somewhere. Underscore fall count. Did that really run for everything? Dang. I guess it's just the test, but so zeros for everything right now. And let's do what? If the diff is 1 or greater, right? Where's our diff? If the diff is 1 or greater, is this for each cube? Are we in a loop? This is for each brick. Okay. If diff is greater than 1, or greater than or equal to 1, I guess, fall count plus equals 1. And then 6, 0, 1, that's 7. That's the number we need. So really what we need here is fallen bricks.iter.map brick.sum. Guess we'll sum into a usize. I keep hitting the wrong keys. Let's sum into usize. I think I'm returning I32s, so maybe we'll just sum into I64s. This is still unit right now. We're trying to return fall count here. Fall count is an I32. We can sum that into an I64, or at least should be able to. Yada, yada, yada. I64 cannot be made by summing an I32. You sure about that? I mean, we could sum into an I32. It's fine. Total falling bricks. Total falling bricks. And then we get 7. I think 7 is the right number. Each brick is 7. So we're just running this on everything. That's it. I'm expecting this to take 10 seconds when we run it, or less, technically. But unless I messed something up, probably not more. We run part 2. 11 seconds. Hey, our calculation was right, at least. Let's see if our other calculation was right. That is right. Okay, great. Wonderful. 22. Done. We benchmarked this earlier. It takes some milliseconds. Not our fastest. I think we probably don't want to benchmark a 10-second runtime. So let's nix the part 2 benchmark in Divan End Criterion, unless we find a better way. Okay, and our benchmark for part 1 is about 8 milliseconds. Reasonably slow. Spent more time visualizing it than actually thinking about how to run this efficiently, so not too bad. Also, just didn't fundamentally write it very efficiently. Like, there's just a lot of collect into this, collect into that, create this map, do this thing, check all the stuff. We're not skipping anything that we could possibly skip. No fancy algorithms today. No looking at input. I'm happy with that. I'm going to move on. One thing I am very happy with, though, is this visualization of all the bricks. I kind of find this really fun to go through. I think I'm going to do at least one more thing. You probably have already seen it if you're watching the video, because I probably showed it at the beginning of the video when I started talking, because it's a fun idea, but I don't know if I did it. So I guess you already know, and I don't. The surprise is for me, not you. But yeah, I don't know. These are all really fun. I had a great time visualizing this today. Just Bevy stuff. Bevy's fun. So let's take a look at what we did for day 22 then. The actual problem is we have a bunch of bricks. We need those to be brought down. So we have all these bricks, right? And we need to show them as if they are lower. So to do that, we start with this input. This input is just a, basically a vec3 range, if you will. I didn't even look, honestly, if like range or anything of the sort is kind of implemented on iVec3s. I'm honestly not even convinced we actually needed to expand all of this, but I wanted to visualize it, so we did, because to visualize it, I need everything. So we take this parser, we do a parser on the left, parser on the right, split pair. Parser's not very complicated today. Separated list 1, line ending brick. A brick parser then gives us back a brick, this struct, which is just cubes. This doesn't need to be a full struct. It could be a tuple struct, whatever. Separated pair, brick end, separated by the tilde. Each of the brick ends is very simple parser, very just like copy pasted it, didn't even think about it that much. We've got X, Y, and Z separated by a comma, and then we do that for each of them. So we end up with these X, Y, Z values for start and end, which we turn into ranges. We turn into iter, multi-Cartesian product that to get every combination of those X, Y, and Z, which gives us all of the cubes for a brick. And we store that in brick and we return the brick. So when we start out here after parse bricks, what we have is every brick with all of the cubes inside of it. Then we sort the bricks because I find it easier to do this algorithm if the bricks are sorted from bottom to top. We sort those by their Z height. The coordinate system we're using is Z up. So if you look at this, which comes from the Bevy cheat book, you can see kind of who uses Z up and who uses Y up. For Blender, they are Z up, Unreal Engine is Z up, and then whether they're left or right-handed. It doesn't actually matter for us whether we're left or right-handed for this problem. So we just kind of like let it do what it do. But Y up is Bevy and Godot and a bunch of other things, including Unity and whatever. So like Z up is kind of outliers, except for CAD software, I guess. But that's the idea. So Z is the vertical direction instead of Y. That is not the thing that I'm supposed to be showing you. So we sort those by Z. So we sort them by the vertical axis, which means that we get the bottom bricks first, which means that we can take all the bricks into a fold and we can move them down one by one. We do this by getting the bottom cubes for any brick that we have. So for this like really tall brick right here, we only get this bottom one. For those minimum cubes, we turn them into vec2s by getting the X and the Y. And then we check to see if there's anything underneath them. If there is something underneath, we increment that by 1 because we need to lay on top of it. And then we calculate the diff between where that brick is currently and where it needs to be. We apply that to all of the cube values inside of that brick. So this whole thing would move down. And then we push the new brick with the new cubes onto our list. This gives us all of the cubes as they've fallen and settled. Then we build up 2 maps. One is a cube to an ID map. We generate the IDs here rather than doing it earlier, just because I was already writing code and I didn't decide to do it from the beginning. So we have this map from cubes to arbitrary IDs that we generate right here. And we have a mapping backwards from the IDs, which are U sizes, to cubes. We use both of these to see if one of them can be dissolved. That is, if it doesn't support anything else. We then go through our logic and we basically take whatever we're working on, whatever brick we're working on, we take the bricks that we are supporting, we look for the bricks that are supporting them, and we count them. If we aren't supporting any bricks, we return true from this filter. If we are supporting bricks, we do the check. Again, we do the check with the min cubes because these vertical slices will collide with themselves effectively and stuff like that. So we don't want to have the second cube up think that it's on top of the first cube. We just want to look at the bottom cube and see if it's on top of this orange cube down here. After we filter out all of those, that's the count. That's it. And then for part 2, we take our code and we abstract it a little bit. So same parsing and everything. And we pull our falling brick. So that logic that we had for falling bricks before with the min cubes and whatnot and the diffs. We add a little logic to boost the count whenever a brick falls. So we know how many bricks moved. And we return that number with our fold. So our fold has changed a signature a little bit, but it's just this I32 that got added. Then we do something really silly. And all we do is for every brick, we try to run the falling algorithm. That's it. That gives us the fall count for all of them because we already wrote the falling algorithm and we just add those up. And that's it. That's it for today. And this is the visualization we built. So we've got a floor, we've got all the bricks, and there's a very long tower going up. And this camera doesn't quite move fast enough for me to show it all, but you can see it moving up and down. This was super fun to build. So if you want to deep dive into the visualization, leave a comment and I might make that video. Otherwise, the code is on GitHub. You can check it out. It's really just placing cubes. I think I'm going to do a little bit more, like I said, before the video ships. So we'll see. You'll either have seen that already or you will not have. I don't know yet because I haven't done it. So I hope you enjoyed today. I enjoyed today. Today was really fun, especially compared to yesterday. So I will see you in the next one. Have a great rest of your night.